stimulate the activation of two factors, which is two factors, actually STAT3 and nuclear factor kappa beta. And STAT3 really you have to have Adam 17 first, which is what is directly activated by angiotensin, and then you have STAT3, and it will also activate nuclear factor kappa beta. And then STAT3 and nuclear factor kappa beta come together, become transcription factors that work together to activate an IL-6 amplifier, which really is more of a cytokine that increases the expression of other cytokines, and then it also increases the secretion of chemokines in non-immune cells. And this process goes on and on and on, because as long as this amplifier is activated, it activates, inflammatory cells. So it activates cells to secrete cytokines. It activates it then also activates let's just say it activates cells, so inflammatory cells and non-immune cells to create chemokines, and then these chemokines go back and feed back into the IL-6 amplifier, into the secretion of IL-6 amplifier. So you have this propagation of non-specific inflammation. Which is quite destructive in a non-specific way. And the reason why it is destructive is because it will just destroy cells, anything really, non-specifically. It won't know whether this is a cell that has been infected and therefore this cell must be targeted. This is a healthy cell that is not infected, therefore it must be spared. No, everything gets destroyed. And given that this is happening, this destruction is happening in the lungs, what we end up having is that, number one, our type 2 pneumocytes get damaged, number one, because they've been hijacked anyhow by the virus, so they're damaged by infection, and they stop producing lung and they also stop producing lung surfactant, and as well they stop becoming progenitors for type 1. So this is no longer there. So we have no mechanism of repairing this type 1 in order to have gaseous exchange. And they need to be repaired because we have a non-specific inflammation that's going on and destroying cells in the lungs that we need. And we will also have increased pulmonary tension, because we have no lung surfactant to keep the alveolar open. So the alveolar is bound to collapse on itself, and the alveolar really is mainly a gaseous exchange. Normally we will have CO2 coming out entering the blood, and O2 coming from the blood to enter the alveolar. But if we haven't got surfactant, then this alveolar start to collapse on itself. And as it's collapsing on itself, there is this non-specific inflammation as well happening, which also then destroys this endothelium here, exposing the endothelium. And as the endothelium is exposed, we normally have tissue factor in the blood, which then binds to the endothelium, eventually leading to the coagulation cascade, the activation of the coagulation cascade, i.e. which forms a clot or a thrombus, which then obviously compromises the VQ, where we would end up with a VQ mismatch, meaning that the ventilation and perfusion is mismatched, therefore the breathing is being compromised. Also, because anyhow there is destruction there, these little alveoli are being destroyed, oxygen is not able to get through, because as inflammation occurs, fluid builds up and escape into the interstitial space on there. So we'll have fluid build up in there, causing tension to rise causing tension to rise against the alveolar. So it's being compressed by this fluid that is building up again around it. And we haven't got any surfactant really to keep it open. So then eventually it means that breathing becomes compromised, so there will be hypoxia. And as well, if there are clots blocking oxygen entering the blood, then there will be very low oxygen in the blood, which is the pathology really that we see where people cannot breathe. Also, we have destroyed the type 2 pneumocytes, we've destroyed type 1 pneumocytes, and the virus itself is propagating and disseminating. And as it's doing that, it's spreading all over the body anyhow, and then then entering, if someone is coughing, viral particles are also being spread out to other people. But the interesting things from a molecular biology point of view is that it has also been discovered that human beings in generally express ACE, in varying concentrations. For example, ACE2. For example, current smokers have high expression of ACE2, while the elderly have low expression of ACE2. And obviously with the elderly, their immune system, because at the moment this is just innate immune system, their adaptive immune system, which is what will be needed for things like viruses, are also compromised due to old age. So really, when they are, say for example, when a current smoker is infected, it means they will have a larger dose of the virus, which means that their mechanism is overused and overwhelmed. All their defenses are overwhelmed and they become severely unwell. The elderly, although they haven't got that much ACE2 expression initially, there is enough time because they haven't got adequate mechanisms to create an antiviral state. So there is sufficient time, actually the elderly people with diabetes, there is sufficient time for the virus to take hold because actually the virus can also upregulate ACE2 expression in order to facilitate its own entry. So because that is happening in that time when this antiviral state is not being induced, there is sufficient time for the virus to take hold and then lead to more pronounced inflammation, which is similar to people who have overexpression of ACE2. They will have more pronounced inflammation simply because their processes are being overwhelmed. They are creating a lot of cytokines and a lot of chemokines. There is augmented inflammation. The elderly, their systems are not so good, and that allows the virus to set in as well and create a similar pathology, really. With these ones, it's more because that initial infectious dose was so small because they only need a small dose to amplify everything. The elderly eventually catch up, but because they haven't got any effective mechanisms of stopping the virus at different stages. For example, all the stages that are needed to come out, enter the nucleus, make more of itself come out, all part of the innate immune system processes are being blocked, are not being effectively functional, and the virus itself encodes mechanisms to block all the stages of trying to create an antiviral state, and it does that by blocking the human body's defenses without blocking itself from multiplying and propagating. Obviously, the reason why the inflammation itself is quite interesting is that in terms of looking at therapy, the recent study from the Oxford group has shown that low-dose dexamethasone can work in people who are incredibly unwell and oxygen dependent because their breathing apparatus has just been destroyed by inflammation. So dexamethasone comes in, stops inflammation, gives the body a chance to start to repair. Other processes that are being looked at actively in terms of preventing the virus itself. So dexamethasone actually treats the disease COVID-19 when it has set in, is to try and block the virus from binding ACE2 by specifically targeting those amino acids that are being specifically targeted by the virus itself, and perhaps also by stopping enzymes such as furin and TMPRSS2 from activating the viral S protein, and then also trying to stop all these processes by inhibiting the processes that are used by the virus. And indeed, things like a vaccine are based on antiviral processes, really. But a vaccine needs the human body itself to work in order to have a vaccine, you need to have functional T cells. And the only, sort of like a concern, I suppose, is that the elderly, their thymus has atrophied with old age. And for a vaccine to work, you need to have T cells that then allow you to start to create antibodies so that they become memory cells that can then fight. You need your T cells to work and then effect antibody creation from B cells, which can then become memory cells. T cells are also specific for identifying cells that have been infected and specifically targeting them. But of course, the virus does stop all of that from happening, and that is part of a more specific immune system response. So, yeah, I suppose really that is quite a brief summary of what the virus does and how it manages to attack the human body and the processes that are currently being looked at in terms of perhaps inhibiting the virus itself, or indeed treating the inflammation that happens and causes the pathology that we see in